My name is Kareem Khalifa, and today we'll be looking at methods of proof with quantifiers.
Here's our plan of attack. We'll go through the elimination and introduction rules for both the universal and existential quantifier. Our first rule is universal elimination. What this says is from a generalization, that is from a universally quantified statement, infer an instance of that generalization. Here's a very simple example. Everybody is happy, so therefore Joe is happy. To represent our premise formally, we would put it this way. For all x, x is happy. Similarly, our conclusion is simply going to be that Joe is happy. I'm going to give you a little teaser of what's coming ahead. Essentially, to prove this, all you would need to do is add that we can get a little bit fancier with universal elimination. Right? For example, we might say all birds are mortal, Tweety is a bird, therefore Tweety is mortal. Note that we have two predicates in this. We have both is a bird and is mortal in this one, so it's going to be slightly more complicated when we formalize it. So first, here's how we'd represent it. We'd say for all x, if x is a bird, then x is mortal. This says all birds are mortal. Then we say Tweety is a bird, and our desired conclusion, our goal, as it were, is that Tweety is mortal. To prove this, we just have to add a few bells and whistles. Right? So note, if we use universal elimination on line 1, we don't just get that Tweety is mortal. We have to be a little bit more deliberate in the steps that we take. So all we do is we drop all the instances of x as well as the quantifier, and we put in Tweety in its place. And so we get if Tweety is a bird, then Tweety is mortal. And once again, we'll appeal to universal elimination, and obviously we're getting that from line 1. Next, to get the ultimate conclusion that Tweety is mortal, we simply do an arrow elimination. And we see that this has really nothing to do with predicate logic. This is just the stuff that we already know. It's arrow elimination, so it's going to be lines 2 and 3. And from that, you can infer that Tweety is mortal. Okay, let's talk about multiple quantifiers now. Here's the crucial thing to understand about multiple quantifiers, is that when you apply elimination rules, in this case universal elimination, you work from left to right, or from the outside in. So you can see with this example, what we're trying to do is prove that from everyone loves everyone, Cleo loves Frida. And so what we have to do is we represent the premise as for all x and all y, x loves y. And because we're moving outside in, we get rid of the x first using universal elimination. Then, to wrap up the proof, we simply get rid of the remaining universal quantifier for all y that's on line 2, and we can get our desired conclusion. Right? So essentially what the reasoning goes as follows. Everyone loves everyone, that's line 1. Therefore, Cleo loves everyone, that's line 2, and you can see that that follows from line 1. Therefore, from the fact that Cleo loves everyone, it follows that Cleo loves Frida, and that's line 3. Okay, let's move to our next rule, existential introduction. On the right, in this case, we start from a particular statement, like Khalifa is a professor, and from that we can infer an existentially quantified statement. In this case, someone is a professor. So pretty clearly, we would represent that as follows. Professor, open parentheses, Khalifa, close parentheses. Therefore, there exists an x such that x is a professor, is going to be our conclusion. And this proof is very simple. All we would do is add on the right-hand column that we're getting line 2 from line 1 on the basis of existential introduction. To round out our understanding of existential introduction, let's look at 3 examples, all of which have the same premise. I just want to show you different variations of a theme so you can see different moves you can make in a proof depending on what you need. So the premise we'll start with is that Al loves himself. So obviously one thing we can infer from this is that someone loves Al, and that would just be an application of existential introduction on line 1. And in fact, all the ones we're going to look at right now are going to be examples where we apply existential introduction to line 1. However, suppose that what we wanted to infer from this instead is not that someone loves Al, but rather that Al loves someone. Once again, this would be an application of existential introduction to line 1, but instead of replacing the first Al in the premise, as it were, we're replacing the second Al in the premise because that is the object of love, as it were, not the subject of love, the lover. Third, we may want to replace both instances of Al in the premise and say that someone loves him or herself. In that case, we would do it as we have on this third example. Right? There exists some x such that x loves x. And once again, that would be a single application of existential introduction to line 1, because all you're doing is you're introducing just a single quantifier, that there exists an x, and just swapping out all instances of al. But any of these 3 examples are legit moves in a proof. Here's a 4th example, which is a little fancier, for reasons that'll become clear in a second. So suppose that we want to infer from the same premise that Al loves himself, that someone loves someone. Here's how we do it. One of the most important lessons that you can draw from this example is that existential introduction, and in fact universal introduction too, works in the exact opposite direction as universal elimination. Remember when we talked about universal elimination, we said you start from the outside and work your way in. Right? You do the exact opposite with introduction rules. You start from the inside and work your way out. And this is because the main operator is always the outermost operator. So in this example, what we'll want to do is introduce y first, because it's supposed to be there is some x and some y such that x loves y. Right? So on line 1, what we've done is we've started off putting the y in the existential introduction there. And then on the next step, what you do is you introduce the outermost existential quantifier. In this case, that there exists an x. And so if we were to talk through the reasoning going from lines 1 to 3, it would go like this. Al loves Al. Therefore, Al loves someone. And because Al loves someone, someone loves someone. And that's basically the reasoning you see going 1 to 3. So I'll wrap up my discussion of existential introduction by showing you how you can use both existential introduction and universal elimination in the same proof in an interesting way. And what I'll do is a variation of the proof that we discussed earlier with universal elimination, which was basically everyone loves everyone, so Cleo loves Frida. And this was the proof that we saw before. Suppose we change the conclusion from Frida loves Cleo to someone loves someone. We can actually keep the proof that we have thus far and just apply 2 instances of existential introduction. And note that we worked from the outside in to get Cleo loves Frida, and now what we'll do is work from the inside out to get someone loves someone. So first move is we're going to add that because Cleo loves Frida, Cleo loves someone. Why is that? Because we're applying existential introduction to line 3. Let's see how we... But of course, if Cleo loves someone, then someone loves someone, which is exactly the conclusion that we wanted. And that's just an application of existential introduction to line 4. Finally, I just want to note something that you'll see a lot in the proofs that are going to come in the rest of the class, basically. And that's what I like to call sort of the quantifier sandwich. If you look at this proof, lines 1 and 2 have quantifiers, then the middle or the guts of it basically is just Boolean or propositional logic, and then we have quantifiers again. Right? So the propositional logic is sandwiched in between the quantified statements. And this is pretty typical because what you're basically doing is simplifying the quantified statement so that you can perform more elementary operations on the propositional stuff, and then you have to reintroduce the quantifiers to get the conclusion that you need. Okay, to wrap up our discussion, I'm going to look at the 2 remaining rules, existential elimination and universal introduction. But because these are a little bit trickier, I'm not going to even try and give you elementary proofs as you would see in, say, something like Fitch using these. I'm just going to give you more of an informal or qualitative kind of feel for that, and that'll be fine for now. We can work on the mechanics in subsequent lectures. So existential elimination is going to be needed for something like the following inference. Some musicians are boxers, therefore someone is a boxer. And in case you don't know, that's Miles Davis. Now when I say it's needed for this inference, I want to be clear this is not an example of existential elimination yet. It's just you can't really make sense of it in a formal proof system without having existential elimination at your disposal. Okay, let's do an informal proof involving existential elimination. So if we look at our first premise, we know that at least one musician is a boxer. That's what that says, but we don't know who it is. Right? So for the sake of argument or illustration or whatever you want to call it, let's just call that person Mr. B. Note that we could have called him just about anything because we're not saying this is actually the boxing musician. This is his real name. We're just doing this as a sort of working hypothesis as it is in our proof. And this is really the crux of existential elimination. If you see what we've done in going in that first line of our proof, what we've done is we've eliminated the existential quantifier that's in the premise of our proof. Okay, and then the rest of this reasoning I think is pretty straightforward from there, right? So we have this guy who we're calling Mr. B. We could have called him Mr. Potato Head. We could have called him whatever, right? But because Mr. B is a musician and a boxer, pretty clearly he's a boxer. That's just and elimination. And of course, since Mr. B is a boxer, it follows from existential introduction that someone is a boxer. So we see that the main move that's happening with existential elimination is really that first move where we just assign a random name to our boxing musician. And that's the gist of it. Okay, now let's look at universal introduction, which, like existential elimination, is a tricky proof, so we're just going to get the gist of it and not worry too much about precise formulations, how it figures in a proof, until later in the class. So the basic idea behind universal introduction is this. You take an arbitrary instance of some given generalization. Now, because it's arbitrary, you can draw a universal conclusion from it. Let's talk through two examples just so you get a sense of this. Perhaps the place you're most likely to have seen universal introduction is in your geometry class, right? So in this example, for instance, we want to prove that the sum of the angles in a triangle is always 180 degrees. What do? We start with any old arbitrary triangle. We show that that triangle sums to 180 degrees. Furthermore, it's important because it's arbitrary. There's no peculiar assumptions made about it. There's nothing special about triangle ABC. And from that, we're allowed to draw a universal conclusion. Here's something that you might see even more colloquially. Suppose someone wanted to argue, you can imagine maybe like a social scientist or a media pundit or something like that, arguing that journalists emphasize previously unknown risks. Right? Well, what they might do is they might say, take any old journalist. That person has an incentive to report on newsworthy events. What are the newsworthy events? Well, the ones that emphasize previously unknown risks. Therefore, all journalists emphasize previously unknown risks. Right? It's obviously very loose, but it's once again an example of universal introduction. So if you recall, what we said is you take an arbitrary instance of a known generalization, and precisely because it's arbitrary, you can draw universal conclusions from it. Right? So in our case, the arbitrary instances are things like triangle ABC, or your typical journalist, and the universal conclusions are things like all triangles' vertices sum to 180 degrees, and all journalists emphasize risks. So why does this work with arbitrary individuals? Because the idea is you could have picked any of the individuals and run the same story with it just as well. So we picked triangle ABC, but we could have done it with BCD, with CDE, with EFG, XYZ, etc. All of the triangles in the world, and it would have worked just fine. That's why the arbitrariness ends up being somewhat important.
Thanks, and I'll see you at the next lesson.
Then use both of the rules that we've learned thus far to establish that conclusion. Of line 2, universal elimination, and appeal to line 1, because you're drawing the specific claim that Joe is happy from the more general claim that everyone is happy.